It's working, right? You can see my screen, right? Okay, so for the outline of my talk, then we have 3 parts. In the first part, then I will try to give a brief introduction about applications and methods of optimal transport in machine learning and data science. Then we will move to the foundation of optimal transport, where we talk about the Monge compilations of optimal transport. Then we also study the Kantorovich relaxations of the Monge compilations. And finally, we also talk about like the popular one, which is the Entropic regularized optimal transport, which was proposed in the recent years to improve the computations of optimal transport. And finally, we try to go into some applications of optimal transport, including the k-means clustering, and also a very popular one in recent years for generative models, which is the Wasserstein optimal transport generative adversarial networks, GANs. Okay, so let me first start with some applications of optimal transport. So optimal transport have been used a lot in the recent years. And one particular area that optimal transport has been a key tool is the generative models. The ideas of generative models, like we have collections of data in high dimensions, like we have images, words, speeches, and then we want to study the underlying distributions of these data. For example, you can see that in the left-hand side, we have the collections of images about animals, buildings, objects. And in the right-hand side, we just have a speech, right? We want to understand what's the key mechanisms that generates these data. But then, because they are very high dimensional, and the traditional tools in statistics and machine learning usually not work very well for this data. That's why we need to use something like very more like more efficient in the cases to generate data in high dimensional settings. And one particular discovery is that optimal transport can be used to define loss function between the boost forward distributions from low dimensional resource space and the empirical distribution of data. And examples of such techniques, including the Wasserstein GAN or like Wasserstein autoencoder. And so later in the lecture, I will try to go into the Wasserstein GAN. Okay, so this is like one applications that have been used in the recent years with the Wasserstein metric optimal transport. Another applications which is also popular, okay, is transfer learning, which is like very popular in the industry. The idea is that you try to transfer our learning that we have from some source domains, right, to the target domains. For example, like the source domain here can be like some kinds of weather, environment, time span that we have for the car, right? We train the AI system here. And then we try to also make sure that when we actually go into different weathers, environment, and time, then the system also able to adapt, right, to these new conditions. And that's why we try to somehow transfer our learning from the some particular weathers, environment, time, to some new environments, weathers, and time, which is like correspond to the target domains. And essentially, this problem corresponds to the problems of comparing two distributions. One distribution is for the target domains. Like that distributions characterize the weathers, the environment, the things like that in the source domain. And another distribution try to characterize the weathers, environments, and time in the target domain. Right? And so optimal transport also plays a key role here to define a divergence between the source distributions and the target distribution. Okay. And also one popular applications of transfer learning is also correspond to like when you try to produce a new iPhone, especially like we try to like develop a new face recognition system, right, in new iPhone. The idea is that like you don't want to collect a lot of data, right? Because when you collect a lot of data, it's very expensive and you don't want to spend too much money for that. And the idea is now like we try to use the old system we have and we try to transfer our learning from the old system to a new one. And this also the ideas of dimensionalization, where we have a lot of like data from the source domains, which is the old iPhones we have. And we try to transfer our learning from the old iPhones to a new one where we have no data, right? We just basically assume that we have no data in the target domain. And we try to make sure that when we try to study the old iPhones, they are they are sufficiently powerful enough to give us like good system in the target domain. And optimal transport, he also offers a resolution to these applications. Okay, so another applications of optimal transport is regarding 3D objects, like 3D objects reconstructions and representation. The idea is that like we have 3D point clouds, right? And it's very important in the autonomous vehicle because like usually when you design autonomous vehicle, then you have a cameras, and the way that it actually captures the objects is based on 3D object, right? It's actually look like 3D objects. And the idea now is like how the car can somehow reconstruct, capture or detect the objects, right? So the idea is like we saw that by using optimal transport here, we also have a good way to reconstruct the 3D, the image, the objects, right? And this also somehow work better than the the popular divergences we usually use, like the transfer distance, transfer divergence, or like other choice of divergences. And here, just like one applications, like I mentioned earlier, like when we try to design an autonomous vehicle system where it try to capture, it try to detect all the objects out surrounding the car, right? Because we have very large scale problems, and we try to reconstruct on the 3D images, 3D objects. So we need to have a very large scale system such that it's able to capture these 3D objects in very efficient way, right? And optimal transport can offer you a very powerful way to do that. So it means like we can somehow hope that optimal transport can offer something very useful for the real applications. And another applications that I also want to mention that optimal transport plays a very fundamental role here is like clustering method, especially like multi-level clustering. The idea is that we have like a lot of images, multiple images, right? In each image, we have like a lot of like annotations. For example, like we have annotations of like of the humans, right? Of humans, of buildings, right? Buildings, humans, and also about the trees. The idea is that we try to study the topics of each image, like whether this image is about animals, is about tree, is about landscape. And the idea is that because each image usually contains a lot of objects, right? But for example, like this image, right? We have cars, bridge, right? Road, something like that. And so to study the picture, to study the topics of this image, we should be able to understand about the clusterings of the annotations of these labels, right? And this also ideas of multi-level clustering. We try to study, understand the clustering of the annotations in each image. And based on the clusters of the annotations, we can have enough information to study the topics of the images, right? And it's also like where optimal transport can play a useful role here, where it try to also can capture the underlying distributions of the clusters in each image and also among images. For example, here we have like we have simulation results showing the benefits of using optimal transport for the clustering problems. So here we can see the 3 clusters from the method. For example, in the first cluster, right, we try to study the clustering of images based on the annotations in the image. You can see that in the first cluster, then all of these images here share the same like annotations, like about a tree. You see that we only have the trees, right, in these images, or we have a car, or we have a sky. So basically, that means like in the first cluster here, the images share the themes about the tree, car, sky, something like that. And then for the second cluster, right, we can see that all of these images here share the annotations about buildings, window, car, and door, right, something like that. So you can see that they clearly belong to one cluster, which is about the buildings, right? And in the third cluster, then you will see that all of these images here share like the similar annotations about like mountains, tree, sky, something like that. So they somehow talk about like landscape, right? So to obtain this cluster here, we actually use the idea from optimal transport, right, to capture the distributions behind these images and try to see like the common the clustering behaviors of the annotations in the images, and then we try to study the topics of the images based on these patterns. Okay. So far we talked about like applications, optimal transport, right, in like generative models, like in transfer learning, in 3D objects, reconstructions, detections, and also in the clustering. But then I also want to highlight that optimal transport is also useful as theoretical tools to understand complex models in deep learning and in machine learning. For example, like in the recent work, we demonstrate that we can somehow represent the convolutional neural networks, right, based on a certain kinds of latent variable models. Like basically, like we demonstrate that we can somehow think about the ReLU, right, in CNNs as the Bernoulli distributions, and the max pooling is just like some kinds of like categorical distribution with 4 values, 1, 2, 3, 4, correspond to move left, right, up and down. And think this way, we somehow can we somehow can think about CNNs in terms of like Gaussian mixture models, where the latent variables here actually correspond to the ReLU and the max pooling in CNN. And by thinking this way, we somehow can think about CNNs, we actually can interpret CNN in terms of optimal transport, because now we can interpret the latent variables, which is the ReLU and max pooling from CNN in terms of like latent variables in Gaussian mixture models. And then we can use optimal transport here to study the latent variables in Gaussian mixture models. So this is how we actually can use optimal transport to understand complex deep learning models like convolutional neural networks, CNN. And besides CNNs, then optimal transport also useful to study many classical machine learning methods, including the mixture models and hierarchical models. Like we can use optimal transport to characterize the conversion rates of the parameter estimations in these models, or we even can perform model selections in these models. Or like we also can use optimal transport to the problems of robust optimizations, right? Basically, like we can use optimal transport to define a perturbed neighborhood of a true distribution, right, in that problems. And these areas turn out to be very popular in the recent years because it can give us very nice properties about the results. And I also want to highlight a few interesting and new ideas, new areas of using optimal transport for analyzing complex machine learning models. The first one, like now we hope that we can use optimal transport to understand the popular step training procedures in the self-supervised learning. Or like in the recent years, they also hope about using optimal transport to understand transformer. Basically, like we try to understand how to match distributions of queries and the keys in transformer to somehow able to improve the performance of transformers in applications. Okay. So I just highlight like how we use optimal transport in real applications and also in theories. Like how can we use the optimal transport to in machine learning in the science general. But then now we try to understand deeply like what is the foundations of optimal transport, why it becomes popular in the recent years, and so like how can we compute that divergence efficiently. And this is also a focus of the second part, which is about the foundations of optimal transport. So we first talk about the Monge formulations, and then we go to the Kantorovich relaxations, and finally we talk about like the Entropic regularized optimal transport, where we actually can use that one to improve computations of optimal transport. Okay, so for the Monge OT formulations, for now, we say optimal transport, I will say it's OT, right? This is what we correspond to optimal transport. Okay, but then just use OT for now, just to simplify my talk. Okay, so optimal transport actually were initiated by the mathematicians Monge, right, to find ways, optimal ways to transport the products, right, between some bakeries to the restaurant under some constraints. For example, like we have like simple illustration here, right, where we try to find a way to move the products between the bakeries and the restaurant. The bakeries here are denoted by P, right? B1, B2, B3, B4, which means like the rest bakery 1, 2, 3, 4. And then for the restaurant, we denote by R, which is like R1, R2, R3, R4, right? Then the idea is like we try to find a way to move the products from the bakeries to the restaurant, right? which is very simple problems. And the rule is like 2 bakeries are going to transport the products to the same restaurant. And we denote the CI trace here to be distance between the bakery BI and the restaurant RJ. For example, like C11 here denotes the distance between the bakeries first bakery and the first restaurant. And C22 here define the distance between the second bakery and the second restaurant. Right? Then the idea is, the goal is now we try to find the shortest distance to move the products between the bakeries and the restaurants. Like we want to find the cheapest way to move the products from the bakeries to restaurants. So these problems seem very simple, but actually lays a very important foundations to many problems in machine learning, right? And here I try to clarify why. So basically, like this problem that we try to do here, we try to find the best way, the simplest way, right? The cheapest way to transport the products from bakery to restaurant. And somehow this equivalent to try to find the best limitations, right, of the bakeries, for example, such that is minimize the total distance that we move from bakery to the restaurant. Right? For example, like here, if we have like N here stand for the numbers of bakeries and the restaurant, right? And permutation here basically like all the permutations of like the set from 1 to N. For example, we have like permutation 3, which is basically like 1, 2, 3, right? And we have 1, 3, 2, and we have 2, 1, 3, and 2, 3, 1, and 3, 1, 2, and 3, 2, 1. Right. So basically, we can see on the possible permutations of the set from 1 to N. Right? And we try to find the best way to match, to actually somehow to match to somehow like move best way to like transport the products from the bakery to the restaurant. And the CI sigma I here basically stand for the distance between the bakery I and the restaurant sigma I, which is like the mapping, right? Like the permutations, right? For example, if we have like sigma to be, for example, we have N to 3, right? And sigma to be like 1, 3, 2. This means like we have sigma 1 is 1, right? Sigma 2 is 3, and sigma 3 is 2, right? So it gives us like one way to transport the mass, right? To transport the products from the first bakery to the first restaurant, right? And the second bakery to the third restaurant, and the third bakery to the second restaurant, right? So in this case, it's like one examples how we transport the products from the bakery to the restaurant. And the challenge now is like this is only one realizations of the permutations, but now we need to find the best permutations to somehow minimize the summations of these distances, like CR sigma. And this problem is actually, if you just search naively for sigma, right, then the complexities of computing of solving that one is actually O(n) factorial, because the total numbers of permutations of that set 1 to N is N factorial, right? So I mean like if we actually use naive search for the optimal permutation sigma here, it's impossible, because when N is like 10, then 10 factorial is already very huge, right? And imagine that we do have like thousands of the restaurant and bakeries, then it's impossible to search for the optimal solution of that amount of optimal transport here. So we need to actually find a better way to match to solve for sigma, I mean like the permutations. And there's a famous algorithms, which is the Hungarian algorithm for graph matching. Because basically, like we can think about this like the Pythagoras graph, where we have the bakeries stand for one side of the graph, and the restaurants stand for another side of the graph. And we try to find a way to match the nodes from the left-hand side graph to the right-hand side graph. And this can be it can be done by using the Hungarian algorithm with the complexities of O(n) cubic, right? Which means like much cheaper, right? Much cheaper than ON cubic, sorry, ON factorial. But then ON cubic is still expensive, because imagine that you have like millions of like bakeries and restaurants. ON cubic is still very expensive. And we're going to talk about how to improve ON cubic later. But then it's a special case of the CI chase of the distance. Like we have one-dimensional, which is not realistic. Just want to give like one special choice of the CI chase here, where we actually can improve further the complexities. Then it turns out that we can further improve computations of the Monge optimal transport here with the complexities of only O and log n. Okay, but only when we have that special choice of the distance CI chase. Okay, and this is not realistic because we never have one-dimensional problems, right? And in real life, it's always three-dimensional, four-dimensional, or even higher. And so this is only just for theoretical interest. But then, especially like ON cubic is the current best one we can hope for, and it's still very expensive. And we hope that we can find a better way to compute, to optimize that one, right? To find optimal solution of that Monge optimal transport. And this one is going to be referred to the Entropic regularized optimal transport later. Okay. And it turns out that we have this form here, but we also want to find a way to analyze somehow. We also want to find another way to interpret that one. And it turns out that we can interpret that one in terms of the probability distributions. For example, we define Pn here to be distributions of the bakeries, and Qn here to distributions of the restaurants. For example, in the right-hand side here, we see that we have Pn here basically correspond to B1, B2, or Bn, just like the support of the distribution Pn, right? And we also have Qn, we have the support R1, R2 to Rn, right? And each of the support B1, B2 to Bn have the same mass, which is 1 by n. And the same thing for Qn. Each of the support here also have the same mass, 1 by n, right? So basically, like we just try to turn the bakeries and the restaurant into probability distributions, right? And then we also define CI chase here, which is the distance between the bakery I and the restaurant chain, right? Then the Monge formulations in equation 1 here, right, can be expressed in this form. We try to find the best mapping T here that mapped RD to RD in such a way that we push forward the distribution, right? We push forward Pn to Qn through T. Right? This is what meaning. And this somehow minimize the integral of the square number distance between x and Tx, right? And x here actually under distribution Pn, right? So in some sense, this is another way we interpret the Monge formulation we have earlier. But then what does it mean to be the push for distribution T sharp Pn to be exactly Qn? So if we take a look at the map here, right, we have two, we have the left-hand side, we have the support of Pn, which is the bakeries. And the right-hand side, we have the support of like Qn, which is the restaurants we have earlier. The idea is now like we try to find a way to map the bakeries to the restaurant, right? And the idea is of T sharp Pn is like find a mapping such that we mapped the bakeries to the restaurant, right? And T sharp Bn and Qn imply that the mapping that we have somehow also match the collections of the restaurants. Basically, like T plays a role of permutation, right? Because basically we try to find permutations of the restaurant R1 to Rn, right? Through the mapping T of P1 up to Bn, right? So in this sense, it basically means like that one somehow implies the kind of like permutations that we see earlier in that form, right? We try to find the optimal permutations that minimize the distance between the bakeries and the restaurants. So this is just like another way for us to interpret that Monge formulations. but then in the forms of distributions. Okay. So, and it's very convenient because that form here allow us to generalize, right? For beyond a simple Bn, Qn, right? And this is very crucial for the applications. And to see that one, then we just basically consider two general distributions, P and Q, right? For example, P can be Gaussian distribution, and Q also can be Gaussian distribution. For example, like P is here Gaussian, right? Gaussian, and it's also Gaussian distributions. And then the most optimal transport between P and Q here can just be defined like what we defined earlier. We try to find the optimal mapping T that push forwards distribution P to Q, right? It's just a way that it minimizes the integrals of the square of x minus t x squared, and where x here actually, where we take the integration of dbx. Right? And it's different from the formulations we have earlier with the distribution data, because P and Q here can be continuous distributions. So the ideas of T sharp P equal to Q here means that if we consider the inverse mapping of any set A under distribution P, then it's also identical to the distributions of Q, the distribution of Q at A, the distribution QA, right? The values of QA. And this holds for all measurable set A of RD, right? It means like we maps any set A here, right, to here, right? And so it's actually quite different from the one we have when we have discrete distributions, because now we have continuous distributions. We try to map like whole set A, right? And that's generalization here somehow more complex, right? More complex than the previous one we have when we have only simple distribution Pn, Qn of the bakeries and the restaurant. But then this kinds of like formulations is very useful for the current machine learning applications, where we can think about P just like the distributions of the images, right? And Q is like just like some kinds of distribution that we want to use to learn the distribution of the images. Right? So they're usually continuous. But then the most formulations actually have some challenges. Basically, like if we have P and Q to be like B and Q have like a density functions, then it's well defined. Or like when P and Q have like uniform weights, like when it's actually have like 1 divided by n weight for the bakeries and 1 divided by n for the restaurants, then we can demonstrate that in this case we can find the optimal mapping T that somehow optimize the Monge formulations in equation 2. But then it's not always possible to somehow find the mapping T when P and Q are discrete distributions. For example, when P only have one support, right? Like for example, here, only one support here. And Q actually have two support, Y1 and Y2, with uniform weight, 1/2 and 1/2. Then distribution T sharp P and Q here basically imply that if we applied, if we try to find the inverse mapping of the single element Y1, which is the part of Q, right? And we try to actually consider the like the measure P at this inverse mapping at Y1, it should be equal to like Q Y1. It's actually from the definitions, right? From the assumption here. But then from the choice of distribution Q, we see that because it's placed 1/2 mass at the Y1 support. So it means like Q Y1 is 1/2. So it means like the probability to measure P places 1/2 mass at the inverse of Y1 under mapping T. However, it's not possible because from the way we define B here, we only can have the probabilities at any support to be 0 or 1. So it's basically impossible to have that one, right? In this case, right? It's mean like in this case, we cannot really find the mapping T, right? right? To satisfy T sharp P just Q, right? So it means like the way that we define that kinds of like OT Monge formulations here is not well defined in this case, because we cannot find the mapping T such that it satisfies the equation T sharp P is just Q, right? So we need to find a way to circumvent that, because when you actually try to define a way to compare the distributions, if it's not well defined under some situations of the distributions, it can be undesirable in practice. And also, like another challenge is like that constraint also nonlinear constraint, meaning the mapping T can be nonlinear. So it can be very non-trivial to solve this mapping T in practice, like because we need to find a way to update T, right? So these two challenges, right? Either like hard to find T, or like T may not exist, right? So these for the two challenges here imply that we need to find a more practical, right, version of optimal transport. And it leads to the ideas of Kantorovich optimal transport, which also give him Nobel Prize in economics. So the idea is like we try to find a choice distribution between two distribution P and Q, right? Instead of like try to mapping T, right? That somehow push the distribution P to Q. So for this, this only thing that we actually different, right, between the Kantorovich optimal transport and the Monge optimal transport. So here, the fact that we consider the choice distribution between B and Qs guarantee that we always can find ways to map the supports of P to Q and vice versa, regardless of the constraints on the distributions, which is very different from the Monge optimal transport formulation. And here we also try to find the optimal choice distribution between B and Q, such that it minimizes the cost matrix. For example, you can think like CXI here, to be like the standard Euclidean matrix, right? But then we also have like under constraint that, but I also consider the integral respect to x and y, e by x and y, right? So this is like the only difference, right, we have so far comparing to the Monge formulations. And the ideas is like for the Monge formulations, we only consider one to one, like we consider like mapping here to here, right? But it's not possible to have this guy, right? Because like when you have this one map to this guy, that is not possible, right? But then for the Kantorovich, then we actually allow one to many, right? So in the Monge, no one to many mappings, right? But then in the Kantorovich, right, we allow like one to many. Right? That is the difference, the main difference between Monge formulations and Kantorovich. Like in this case, because Monge actually doesn't allow us to split to actually allow us to map that blue point here to 2 points, right, in the right hand side. But then for Kantorovich, then it's actually possible to do that. And this also the ideas of Kantorovich. We allow to transport to split the mass of 1 point, right, of P to like many points of Q. So that's also solve the issues of the Monge formulations. And we can demonstrate that under some assumptions of the distributions, then the Kantorovich optimal transport and the Monge optimal transport are similar. And the pi here in this form 3 here also count to be transportation blend, right? Which is very popular term that we use in machine learning nowadays. So to see like how we actually can define optimal transport between two distributions, then we can see some examples. For example, like when P only have one support and Q have like M support here, which is theta 1, theta M, then we can define the optimal transport between P and Q, right? Which is a summation from Qi multiply the cost metric between eta and theta I, right? Because in this case, when you consider phi between the distribution between P and Q, right? Then it's also implied that phi I is always Qi for that case, right? So I mean, in this case, we only have one choice of phi here, only one choice. That's why it exactly is this value, okay? But then when we have like multiple supports of P and multiple support on Q, right? We have like eta 1, eta n for distribution P and theta 1, theta m of distribution Q. Then we also can, based on the formulations of the Kantorovich optimal transport here, we also can define that to be the minimum if we want to find the best matrix, right? Because in this case, we try to formulate the problems of finding the joint distribution between B and Q's, and finding the matrix of dimension pi here of dimension n times n, right? Such that it's minimize the summations of pi ij's, right? Multiply the cost metric between eta I and theta j's, right? So to see this clearly and satisfy the constraint as well. So it can be like a bit like scary to see, like, because we have so much constraint. But then to understand one, we can take a look at the right hand side illustration here. Basically, like we have like a similar examples where we have like, oops, sorry. Oh. We have similar examples where we have like n to be 4 and m to be 6, right? And we see in this case, the pi here basically just like a matrix of 4 times 6, right? For 6 rows and 4 columns. And should be like, okay, that's enough. And we try to find pi here, such that the rows, the column sum here is B1, the first column sum B1, and the second column sum here, the row second sum is B2, right? And the third column sum is actually B3. And also like the first row sum is actually Q1, and the second row sum is Q2. Basically, like this is also what the constraint means. We try to make sure that the row sum and the column sums of the matrix by here, which is the plan we want to find, actually match the weights of distribution P and Q, right? So in some sense, this essentially the way we actually define optimal transport between two distributions through the Kantorovich formulations. And if we actually consider a more mathematical way to like formulate that one, that is actually just like inner products between a cost matrix C and pi. And this one basically means like the summation of Cij's by ij, right? It's like it's like consider inner product between cost matrix and the bland pi. And this assumption here, this constraint here basically comes from this, basically mean these things, right? It mean like the row sums and the column sums of matrix pi here actually equal to the weights P and Q, right? And the problem phi here is in fact a linear programming problems, right? And to simplify the result, the representation, we also define P here to be the transportation polytope, right, of that linear programming, where it consists of on of the matrix n times m, shows that on the elements of pi is actually non-negative, and the row sum and the column sums of pi actually P and Q. So it means like we try to minimize the inner product between the cost matrix and the bland pi, such that it belongs to the polytope P, right? And from the language of linear programming, then the optimal solution is obtained at the furthest and extreme points of that polytope, right? But then we can demonstrate that as long as pi is an extreme point of that polytope, then pi we have at most n plus m plus 1 non-zero entries, right? Because pi actually is a matrix n times m, right? But then we demonstrate that only at most m plus m plus 1 non-zero entries, right, of pi. And the idea is this proof actually in this reference. So I'm not going to go into detail of this reference here. So the theorem 1 here gives us the ideas of how to search for, how to develop algorithms to search for the optimal extreme points of the polytope. Because we know this actually has this property, right? And you see that one, we also need to consider the dual form of the linear programming phi here, which is this guy here. So we can demonstrate that the optimal transport between P and Q's is essentially also equivalent to find the optimal U and V in that set RC here, such that it maximizes the inner product between U and P and V and Q, right? Where that set RC here correspond to on the pairs U and V in Rn, Rm, such that the U multiply 1m transpose plus 1n V transpose actually less than C. That's not to C, right? That's one. This one is a matrix. One is a matrix n times m. Okay. And when you say like a less than or equal to b, it means like a I chase less than p I chase for on I chase. Okay. This is how we mean when we say that matrix A less than or equal to matrix B. Right. And so this is the way that we derive number one. It basically stand for basically just standard way using the Lagrangian function of the optimal transport formulation in equation 5. So I'm not going into details about that. But then that dual form here, this is a dual form, right? This is a dual form. It's very useful because this somehow means that we can translate the problems of finding the optimal extreme points of the original problem phi into also finding the optimal U and V of the dual form. And somehow it turns out that if we have pi star is the optimal solution of the primal forms, and U star and V star to be the optimal solution of the dual form, then we have these relations, right? Pi I j star multiply UI star plus Bj star plus Ci j 0. And this actually comes from the KKT conditions, right? But then I'm not going to detail the condition as well. You can take a look at the Wikipedia. But then this basically means like we can find the connections between the optimal solutions of the primal forms and dual form. And it demonstrates that if we have pi ij star bigger than 0, then it's also implied that we have ui star plus Bj star minus Cij 0, right? And this exactly means like if we have this guy less than 0, then we have pi ij star is 0. So this gives us like the way to determine like pi star and u star v star. And I mentioned earlier, the way that we try to find the extreme points on the polytope here, we try to develop some algorithm for that. So we try to do that one through the dual form. And now we already established some connection between dual variables and the primal variables, right? So we try to find a way to leverage that insight to develop algorithms. And this also leads to the following notions of the complementary slackness. So we say that a matrix pi and the factors u and v here are complementary with respect to cost matrix. If as long as this guy, as long as the pi I chase here is actually positive, then we always have pi I mu ui plus v chase plus ci chase 0. And this actually motivates by that condition we have earlier here, right? Because you try to find optimal solutions, right, of the dual form and the primal forms. But then here you try to make sure that for any matrix pi and any factors u and v, they also have some similar behaviors like the optimal solutions. And then it turns out that if the plan pi of the polytope P and the factors u v of the set RC here are complementary, then they both the optimal solutions of the primal form and the dual forms. And that's number 3 here are it's very useful to develop the network simplex algorithms. The idea is that we just basically like initialize, right? Initialize any extreme points, right? And then we construct the corresponding complementary dual variables U and V, right? And then there are two possibilities. The first one is that if that pair is feasible, right? If that pair is feasible, then I mean like U and V actually belong to this RC set. Then we know from lemma 3 that both phi and UVs are optimals. So we stop the algorithm here. But then if that pair is not feasible, it means like UV may not belong to this set. Then we develop a modification of phi such that it remains in the polytope, and also the associated like complementary dual variables become close to the belong to the set RC, right? So basically, we try to find ways such that pi, right, to make sure that pi and UV become close to become optimal, right? And by doing that algorithms, we can demonstrate that the optimal complexities of using that kind of network simplex algorithm is n plus m multiply nms, right? And also multiply the block terms, which I ignore here. So basically, we only care about terms. So when m is equal to n, then we have like the complexity become like O(n) cubic log n, right? Which again, not very also very expensive when n is very large, right? Therefore, we also cannot use network simplex algorithms, right, for scalable computations, right? And this also motivates the ideas of the entropic regularized optimal transport in the recent years in machine learning. So the ideas of the entropic regularized optimal transport, like we try to regularize the objective of the optimal transport by using the entropies of the transportation plan pi, where eta here is just like the regularized parameters, and the h pi here is basically just like the traditional entropies of pi, right? And here also the polytopes p, right, between b and q, just like the polytope between b and q, what we defined earlier, right? And the idea is that we actually do such regularization because we can make sure that by doing such regularization, then the entropic regularized optimal transport become eta strongly convex function, right? And it's because the function minus h here is actually one strongly convex. And it's because strongly convex, it means that now we actually have a unique optimal blend pi star eta for the entropic regularized optimal transport. And the uniqueness of pi star eta here is very important because it's basically mean like we can develop very good algorithms to somehow find pi star eta. And before going to the algorithms, I also want to give like a very simple properties of the entropic regularized optimal transport. Basically, like when the regularized parameters go 0, then we can demonstrate that the values of the entropic regularized optimal transport converge to the two values of optimal transport between P and Q. And also the optimal blends here also converge to the optimal blend, right, of the original problems. Okay. But then when eta here go to infinity, then the optimal transport, entropic regularized optimal transport between P and Q here converge to the inner product between C and the product measure between P and Q, right? And the same thing also for the blend pi star eta here, also converge to the product measure between P and Q. So it means like when you actually let eta sufficiently large, then we can think that distribution P and Q are independent, and we actually don't learn much from consider their divergences. So ideally, we want this case, because this case means like we can somehow make sure that we can approximate the original values of optimal transport between P and Q. But then how can we develop the algorithm for solving the entropic regularized optimal transport? And this is also the idea of Sinkhorn algorithms, right? We try to demonstrate that we can develop a very simple algorithm to solve the entropic regularized optimal transport. But then there are still some challenges for developing the algorithm here, because the Bramble form here, which is here, the Bramble form here, is still very like complex because we still have many constraints, right? Many constraints for in the many constraints, and it's still non-trivial to solve the primal form directly. And the idea is now that we actually try to derive the dual forms of the entropic optimal transport, and to see how we actually derive the dual form, then I try also to highlight a few key steps here. First, we try to get the Lagrangian functions of the primal forms. And basically, because we have such problems, we have such max of the pi in the PQ, right? For the original problems, right? You see like entropic optimal transport eta, right? And then we try to move this one up here, right? And that's here. And it's by including the extras UV, right? It's called the max, right? And we have that's in the product between U and the first constraints, and V and the second constraints, right? This is how we usually define the Lagrangian functions for constraint problems, constraint optimization problems. And then it's mean like this guy, entropic regularized optimal transport here going to be equivalent to that's problems, right? Mean max, right? Mean over pi and max over U and V. Then from equation 8 here, we can exchange the order between mean and max because this is basically like a convex concave problems. And we consider solving that problems here. Consider finding the best pi that going to minimize that objective function. And that function L here, we define it to be like L by UV. And that function is actually Charlotte convex and differentiable on pi, right? So it's mean like we actually can solve the gradients of that function to find exact forms for the optimal solution pi for solving that for minimizing the function L by UV. And we take gradients, and after some computations, we can demonstrate that we have pi I chase of this form, right? So this means like this is the form we have for the optimals pi to minimize the function L by UV. Okay, and then plugging in this pi here to the equations 9, we derive this equivalent form, right? Then by using that pi I chase here, and we have this equivalent forms of equation 9, right? So this you see now we actually have no constraint, right? No constraints on UV, right? Which is very convenient for optimization, right? And we also do some transformation to further simplify that objective function. We actually do such transformation here, okay, to further simplify that dual form. And eventually, by doing such transformation, we have the mean of U and V. U and V are dual variables, right? U and V are dual variables of that whole sum here, of that function here. And this is actually unconstrained convex optimization problems, right? And this means like we can actually use a lot of optimization method to solve it. And the popular choice for the optimization algorithm here is Sinkhorn algorithms. And before going to the Sinkhorn algorithms, I also want to state the relation between the optimal solution of the primal forms and dual forms. So the primal form here is for the entropic, right? Optimal transport with eta, and the dual form here is that guy, 11 here. Then we can demonstrate that if pi star is the optimal blend of the primal form 7, and U star V star here is the optimal solution of the dual forms, then we have pi star I chase here exactly exponential of UI star Vj star minus Ci chase by eta. This actually comes from our form here, okay? After we also transformation of U and V as well, right? So this here gives us like how we can actually derive optimal solutions of the dual and primal forms of the entropic regularized optimal transport. It means like if we can solve for UV Yeah, it's been like we also can solve for pi, right? From that results. So it's very important. I mean, like now we actually focus on solving the dual problems and develop some algorithm for that. And then we can go back to the primal forms. Question? Okay. Now, given that now we also want to make sure that I also want to make some connection here. So if we actually define k here to be the exponentials of minus c eta, which means like ki chase is basically exponential of minus ci chase by eta, right? Where k here basically ki chase, right? It's a matrix, right? Then we also can somehow write out the result we have this corollary one here in this form. Pi star is just like the diagonal matrix of u star multiply k multiply diagonal matrix of v star. This one mean like we have like a matrix where we have on of the elements of u star in diagonals. And the same thing for that one. It's been like we have a diagonal matrix where on elements of v star on also in diagonals of that matrix. And that form actually very important because we have the constraint that pi star 1m here is p and pi star transpose 1n is q. So basically, when you actually plug in multiply 1m to this equation, right? We have this equations here. This one leads to these guys, and the same thing for this equation is also leads to that equation here. And these problems actually refer to a matrix scaling problems, which is popular in theoretical. Let's say which is actually like let's say in computer science, right? Yeah, and this problem actually quite challenging to solve because basically we try to find u and v, right? We try to find u and v, just that we have two equations like that, right? We try to find u and v, u star and v star, just that diagonal u star multiply k multiply v star, and diagonal v star multiply k transpose u star actually satisfy the equations. And we demonstrate that the Sinkhorn algorithm is an algorithm for doing that, right? Do you want to set one like I define this is like the dual function, right? Dual function f, right? Basically, it's like correspond to the function here. It's fuv here, right? And we try to minimize u and v about fuv, right? So we try to develop a blockwise coordinate descent method. Mean like if we fix u and we update for v, and we fix v and update for u. It's been like we try to first fix v and solve for the gradients of u of f, and then we fix u and we solve for the gradients of f. And by some direct commutations, then we can demonstrate that the gradients of f with u, right, lead to that kind of update. Okay, this is how we update u in the Sinkhorn algorithms. And the same thing, if we actually take gradients of v and let this one to be exactly 0, we also have that updates for v. So this means like we have the following algorithm, which is Sinkhorn algorithm. Like we first initialize u0 and v0 to be exact 0. Then if the iteration numbers is even number, then we basically fix v. We actually fix v, right? Fix v and update u, right? And update u here actually based on solving that gradients with 0, which we have this form, right? That's why we have ui t plus 1 here, the block bi minus block of exponentials of b j prime t and the cost matrix, which is come from that equation, right? And the same thing here, when t here is just an odd number, then we update v and we fix u, right? So we actually alternate the update between u and v, right? Basically for our idea earlier. And we keep doing that until the algorithm converge to some point. And in some sense, we also can describe updates here in this form. You have ut plus 1 is just like p divided by k multiplied vt, where k here basically exponential of the cost matrix divided by eta we have earlier. Right? And that's notation P divided by K V transpose mean like we have like PI divided by K times V choose I, right? For on I. The same thing for PT plus 1. We also can think it's like a Q divided by K times UT plus 1. Right? And when T goes to infinity, then we have UT and we have the updates from Sinkhorn algorithm converge to the optimal solution. We like, right? The updates from Sinkhorn converge to optimal dual variables, right? It's what it means when we let number iteration go to infinity. But then the question now is, what's the conversion rate of a Sinkhorn? Like how many iterations that we can guarantee that the updates for Sinkhorn converge to closer to the optimal solution, right? And to understand one, we actually need to introduce a metric to capture the gap between the solution of the updates of Sinkhorn and optimal solution. And this stands for the Hilbert's projective metric. Let's see, like for any vectors u and u prime, we define the Hilbert matrix between u and u prime just to be like the log max of ui multiplied uj prime divided by uj multiplied ui prime. And it's considered over on the index I and j. Right? It's basically considered the scaling of the vectors u and u prime. And we can demonstrate that the Hilbert matrix is also distance on the projective column, right? It means like when the Hilbert matrix between u and u prime is be 0, then we have u to be r multiplied u prime. It means like you can scale u to u prime through the r. And also we can have a triangle inequalities as well, right? And then given these properties, then it's very useful because it can be used to like understand the convergence. Because when you have a triangle inequalities, then it's very useful to establish the conversion rate of the updates of Sinkhorn algorithm to the optimal solution. And another important property is like we have the scaling properties of the Sinkhorn updates. Like basically mean like if we have the Hilbert matrix, then we scale each direction, each vectors v prime by a matrix k prime. Then the Hilbert matrix between the products between k prime v and k times k prime v prime actually can be upbounded by the Hilbert matrix between v prime. And it's actually the contractions, right? It's actually like the constant that actually captures scaling. And I'm not going into details about the constants. This can be a bit complicated, but like we can guarantee that by k prime here less than 1. It's very important because later when you go to the Sinkhorn algorithms, we can demonstrate that if use t and vt's are updates from the Sinkhorn algorithms, then the gap between the updates of u and u star actually less than equal to c multiply lambda k to 2t, right? And lambda k is here less than 1 and defined in theorem 4. The same thing for the distance between v and v star, sorry. Bt and v star also c multiply lambda k to 2t. So it's mean like we have the linear convergence of Sinkhorn. I mean like if you run Sinkhorn algorithm, then it's going to be converged to the optimal solution very fast. For example, we just take a look at the simple illustration here. We see that the Sinkhorn algorithm only take a few steps to converge to the optimal solution, where the red line here corresponds to the optimal values. You see that one, in this case, Sinkhorn take a few steps to converge. And it's also somehow verified by our theory in theorem 5. It means like by using Sinkhorn algorithm, we can actually have a very fast convergence towards the optimal solutions, which is very nice. And the linear convergence of Sinkhorn also gives us the idea about like how can we use that linear convergence to approximate the optimal transport, right? Because eventually our idea is like we try to find an approximation of optimal transport, and we show that by using Sinkhorn we can have a much more scalable commutations of optimal transport than what we have earlier by using the network simplex algorithms. So here we just basically say, okay, we quantify a planned 5 bar in the polytope P. Okay, you can find definition of P in that slide 26 here. Just that we have this constraint. So we basically try to find the approximations of the optimal transport values, right? And by part is what we want to find. And if we define UT and VT as the updates of step T from Sinkhorn algorithms, then we can also demonstrate that this is the relations between UT, VT, and pi t, which is the plan we have T from UT and VT, which is which is updates of Sinkhorn, and pi t is like updates for the plant for the optimal transport. Then we can demonstrate that by using Sinkhorn algorithms, by choosing the regularized parameters at this form, like eta approximately like epsilon divided by logs of max between n and m, right? Then we can approximate the optimal values of the optimal transport within t at the orders of 1 divided by epsilon square number of iterations, right? We need to have that number of iterations to make sure that we can have that inequalities. And that implies that because each step of Sinkhorn algorithm requires max of n and m square number of operations. So it'd be like the total complexities of a Sinkhorn algorithm for approximating the optimal transport is max n m square, right? Multiply the basically like O's of max n m square divided by epsilon square, right? This is the complexities of the Sinkhorn algorithm for approximating the optimal transport. So if you remember earlier, for the network simplex, right, we have O of max n m cubic. But then by using Sinkhorn algorithm, right, we have like O max of n m square divided by epsilon square. So it's much more scalable because now we only have max of n m square, right? Which is much more scalable, right? And it's also the reason why optimal transport become very popular now, because we're able to develop an algorithm to improve the scalabilities of computing optimal transport. And it's also the reason why we only talk about applications of optimal transport now. And two applications that we care about, first is the k-means clustering, and the second one is what's the GANs. Okay, so for the k-means clustering, I will try to go briefly k-means clustering and try to focus more on GANs. So for k-means clustering, perhaps you already know, like we try to find a way to cluster data, right, into like some clusters, right? And for example, like we have like data like images, right, words, something like that, and you want to cluster them into some topics or like some topics or like some categories, right? And the idea means like we want to find k-centroids, centroids data based on the similarities of the data in this cluster. And the objective k-means basically like we try to find the centroids mu1 to mu k, such that it minimizes the summation here, right? And basically, for example, on the left-hand side, we have as our data, right? It's our data, but then we want to find how we want to find a cluster of this data, right? And somehow, like by using k-means, and these guys here, red color, green color, and purple colors actually correspond to mu1. It's actually mu1. It's actually mu2. Actually mu3, right? Basically, we try to find a way to cluster data based on their similarities. And this is how we actually capture their similarities. We find the closest centroids to data, right? And but then the objective k-means actually not non-convex, right? Because we have that mean, right? That mean term here. So it's mean like it's actually non-trivial to solve. And somehow there's a very useful insight. If we define CI to be on of these centroids, that's close to like, sorry, if we define CI to be on of these data, that's close to the centroids UI, right? Then we have the unions of all of CI to be the whole set of data points from 1 to n, right? And then for each cluster of CI, right, then the optimal solutions to that like problems here, we basically just like the average of data points. Right? It's basically like we try to solve the centroids of the data points. Right? We solve the centroids of data points in CI, right? And so it's actually give us very useful insight. I mean, like in this case, to find the optimal centroids of a k-means problem, we just need to search for all of the possible partitions C1 to Cn, right? So it's actually CK. First of all, on the possible partitions C1 to CK, and then we basically compute all of the C centroids based on this formulation, right? Then we actually can find the optimal centroids by doing that. We try to search for on the possible partitions of from 1 to n into k subset, right? But then it's actually practically expensive because the number of partitions of the set 1 to n into k subset here actually just a Stirling number of the second kind, and it's actually exponential in n, right? So it means like even when n only 100, it's already extremely expensive, right? So doing that's not going to be practical, right? That's why we need to find a way to update the centroids of the k-means, even though we only have the local minima. And this can lead to the standard, very popular k-means algorithms, where we try to initialize the centers mu1 0, mu2 0, and μk 0 of k-means problems, right? And then for any iteration, we try to compute the cluster assignments, right? Basically, like we try to find the cluster on data points that close to the centroids mu(i), right? Then we update the centroids as we see earlier. Right? We can find all data point that centroids and the centers. Then we find all data point in that set, and then we try to update the mean of these data points. So we have a new updates for the centroids based on the data point that we have, and we increase iteration number, and we also try to keep updating that the centroids. And so the k-means algorithm, right, guarantee local minima, right, of the k-means problems. But then if we don't care too much about finding the global minima, then the k-means algorithm actually very efficient. And we also can demonstrate that after each step of the k-means algorithm, then the objective values of k-means, right? This is like the objective values of k-means, right? We are guaranteed that it's always decreasing when we actually increase the number of iterations. And because we only have finite number of ways to partition any data point to k subset, it means like the updates of k-means algorithm, we convert to local minimas of the k-mean objective function, right? So it's actually okay because this one is very fast, right? So if I mentioned, if we don't care about the global minima, then k-means can be an efficient and useful algorithm. But then it's not main focus. Our main focus now is like we try to interpret k-means clustering as an optimal transport problems. And because recall that we have this is like the k-mean, right? So k-means basically like we try to find a mean, right, of mu1 to μk of 1 5 to n, sum from 1 to n, right, of the mean of the on the centers, right? So we can also demonstrate that the k-means here actually can be interpreted based on optimal transports. And this actually very deep connections that allow us to develop a lot of new ideas for applications. But before going to the connection here, we also need to define some key notations. And the notion that we care about is the Wasserstein metric of the second order. And it's also a special case of the Kantorovich optimal transport that we defined earlier. So we say that the second order was diametric is basically also similar to the previous definition we have, except that now the cost matrix Cxy with 2 to be the standard Euclidean distance, right? So this is the only difference between, it's only the thing that we have in the Kantorovich optimal transport. So it's just like the way we define the Kantorovich optimal transport with a special cost matrix to be the Euclidean distance between the data points. And then we can demonstrate that the Wasserstein matrix of second order is actually also satisfied to be a metric, right? I mean, like if we have Wasserstein metric between two distributions to be 0, then the distribution also identical. And also we have a triangle inequalities with the Wasserstein metric of second order. I mean, like if we can see that 3 measures B, Q, and R, then Wasserstein metric between B and Q, plus the Wasserstein metric of second order between Q and R, is always at least are equal to Wasserstein metric of second order between P and R. And the proof of theorem 6 here can be found in the book by Villani, right, 21 here. I'm not going into details about this proof. But then these properties of second order Wasserstein metric is very crucial to establish the connection between k-means and Wasserstein metric. So we can demonstrate that if we define Pn here to the distribution of data, right? Basically mean assign one from the end uniform mass for a data point. Then the k-means problems, this k-means problem here, k-means, right? Original k-means, right? It's actually equivalent to finding the optimal measures G with at most K, with exactly K support, right? Exactly K's atoms that minimize the Wasserstein metric between G and Pn, which is the data distribution. So basically, like this is very deep, right? Very deep connection, right? Because somehow you connect problems of finding the minimal cost, right, of assigning the data point to the closest centers to problems of minimizing the second order Wasserstein metric between the data distributions and some measures. Exactly K support, right? This insight here is very crucial for us to develop the understanding of the optimal centers that we obtain from k-means. And also it gives us the idea is that optimal transport or Wasserstein metric maybe is a very natural metrics for the clustering data. And it's also led to a lot of interesting clustering method in the recent years in machine learning. And I'm not going to go into details of the purpose 2 here. We only focus on purpose 1, the lecture. But for purpose 2, then I mentioned there are a lot of interesting ideas based on optimal transport in the recent years for clustering data. And this also is already based on that connection I mentioned in theorem 7. This connection is very crucial. But now we want to see, like, if we want to understand the behaviors of the centers of the k-means, then the theorem 7 here is very useful. Like, so if we have data x1 to xn IID data from some distribution B star, right? And we have mu1 hat to mu k hat to be the centroids of the k-means problems. Then the question now is, what are the limiting distribution or limiting points of the centroids by mu1 hat to mu k hat when the sample size go to infinity? And this is actually a non-trivial question because it's not clear like what is the guarantee for the centers, right? And optimal transport is very useful for very useful to answer the questions. The idea is like we define G and hat here to be the optimal solution that minimize the Wasserstein metric between B and G. Like the right hand side, that's if the right hand side is 1. We try to define G and hat here to be the corresponding optimal measures for this real equation here, right? Then we demonstrate that we want to understand the limiting distribution of G and hat, because G and hat here, they captures both the centroids, optimal centers of k-means, and optimal ratios, which is like the proportion data that are closest to its centroids. And to understand the convergence of the centroids of k-means, right, we need to understand the behaviors of the distribution of G and hat, right, which is the optimal measures that minimize the Wasserstein metric between data distributions and G. And we can demonstrate that under some assumptions of B star, the two distributions of data, then the Wasserstein metric, the G and hat here, which is the optimal distributions that minimize Wasserstein metric between their distributions and G, always converge G star, where G star here basically just like optimal solutions that minimize optimal measure minimize Wasserstein metric between B star and G, right? So this actually means like eventually what we're doing in k-means, we try to estimate the centroids, right? That's somehow partitions the B star, which is the two distribution of data, right? In particular, it means like if we have G star to be this form, like Bi star and Mu I star to be the centroids and Bi star to be the mass, that's going to minimize a problem, right? Then the centroids from k-means, this is from k-means, right? We converge to the support of G star. I mean, like it converge to a Mu1 star, Mu2 star, and Mu K star. The same thing for the weight and masses of like G and hat. I mean, like the proportions of data, P1 hat, B2 hat, Bk hat, also converge to the corresponding weights and masses of G star. So I mean, like eventually, what we do in k-means, we try to recover the centers and the masses that we try to partitions. We try to like we try to somehow like partitions B star, right, to distributions into K cluster. And so we see that without using optimal transport, it can be quite non-trivial to establish such guarantee. And through the connection between k-means and optimal transport here, we can easily find the connections. We can easily understand the behaviors of our centroids when we have infinite number of data points. And that's also is motivation for many methods, clustering method, people use nowadays based on optimal transport, right? Because optimal transport here actually is a natural way to define the cluster of the data points. Right? Okay, so this is also the first motivation, the first applications where I want to demonstrate that we have a very natural way to do clustering based on optimal transport. The second applications I want to mention now is the generative adversarial networks, GANs, which has gained a lot of attention in the recent years, thanks to its like impressive performance in generative models. So recall that for generative models, we try to learn the distribution of data, which usually very high dimensional settings. Right? For example, like we have like 10,000, 20,000, even like 100,000 or 1 million dimensions of data, of images. So for this task, right, there actually are many approaches to generate data, to actually learn distributions of data. We have like non-parametric approaches or like parametric approaches. So for the talk today, for a lecture today, we only focus on the deep learning models, right? And particularly we only focus on the generative adversarial networks, GANs. But then I also give you like a little bit survey here when you also can take a look later about other approaches, right? Like you can take a look at like about like the Bayesian hierarchical models or the Bayesian non-parametric models. But then for the talk today, we only focus on deep learning models. So eventually, generative adversarial networks is just an examples of the implicit methods. I mean, like we don't care about estimates the density function. We only care to make sure that distribution data it goes to some distribution by using gas, gas. And the reason that we do that because we want to allow an interpolation across images. Like doing that also may able to give us some kind of variation data. Like we may have some kind of balance that we don't see from images by doing the implicit method. And this is also very different from the variational autoencoder, which is like an instance of the explicit method, where we try to obtain an estimation of answer function. And the recipe of the implicit methods is like that. We generate some latent variables z from distribution bz, for example, like action distribution. And then we consider data generation distribution dvc. Basically, we boost forward distribution of z through mapping tv, right? tv especially play the roles of boost forward distribution, boost forward mapping, right? And that is now we want to make sure that dvc here is close to p, which is our data distribution, right? Yeah. So we only care to make sure that the boost forward distributions of z here through the mapping TV here is close to the true distribution p. And it means like we need to define some divergence between dvz and p. And from the original papers, GANs, then the choice that the authors use is actually based on the transient Shannon divergence. Basically, they try to minimize the parameters part of P between the Shannon divergence, between transient Shannon divergence between DVZ and P, right? Where we define the transient Shannon divergence between DVZ and P to be the KL divergence between DVZ and the average of P and DVZ, and also plus the KL between P and the average of P and DVZ, right? So this basically makes sure that it's actually symmetric, right? And it turns out that using the transient standard divergence also allow us to interpret that equations 14 here in the sense of like minimax game. I mean, like if we actually know G to be TP, then we can demonstrate that the problem 14 is basically just like a min-max game, where G here is just generator and D here discriminators. And we try to see the expectation of X come from data distribution of log dx, plus the expectation of Z come from the latent variables, right? Log of 1 minus dgz, right? And the equation 15 here is just an examples of non-convex, non-concave minimax optimization. And you see, non-trivial to solve. And active research, right? Still active research area nowadays, like what kind of guarantee we have for this non-convex, non-concave minimax optimization, right? And in fact, based on equation 15, then we also can have a very interesting way to explain that. So like imagine that we have two players plays the minimax game. One player plays the discriminators and one player plays the generators. So basically there's one guy plays the generators and one guy plays the discriminators. So the discriminators try to maximize the log likelihood of the binary classifications problems of detecting the real and fake data. And why fake data? Remember, this guy actually generates the fake data, right? So what points like T here actually TV, right? That's why GTZ actually a TVZ, right? Right. So that is like the discriminator try to maximize the chance that we actually can detect the real effect data from the generators. But then the generators, right? These here, maximize, right? The generators actually try to minimize this guy, try to minimize the probabilities that the sample be detected to be effect data by the generator. Sorry, by the discriminators. So basically, like one guys try to maximize chance to detect the fact data, and another guys try to minimize the chance that the discriminators can detect it to be a fact data. Right? And that's actually give a very interesting way to understand GANs. Right? Basically, like we try to make sure that one guys can maximize the change. We actually can maximize. We actually can minimize. We actually can find the optimal mappings, right? Just that the data we generate from that somehow can be get closer to the distribution. Okay. And the training procedures and images generated from GANs, so you can actually refer to the original papers here. I'm not going to go into details about these procedures and also the images. I also want to motivate the reason why we use time metric here. So recall that we only use like transient standard divergence, right, for GANs. Then what's the challenge with the transient standard divergence? The first one, like if the fact data distributions and the rule distributions, they have a disjoint support, or like one is continuous distribution and another one is discrete distribution, then the transient standard divergence become problematic. So to see that, then we can see the very simple examples where we have a TBC here, basically just like VZ, where C here comes from the uniform distribution, and P here basically is like just like 0 and the uniform distribution of 0, 1. Then we can demonstrate that the transient standard divergence between TBZ and P here is simply log 2, right? As long as the parameters is not 0 and becomes 0 otherwise. And this means like the transient standard divergence is not continuous, right? At the 2 parameters, okay? Because in this case, phi is 0 is the 2 parameter. Okay? And you hope that we actually can recover the 2 parameters from minimizing the transient standard divergence between TBZ and P. But somehow, because the transient standard divergence is not continuous at the 2 parameters, and take the constant values, which is log 2, when phi is not 0, it means like gradient descent method cannot be used. So this can actually undesirable in practice, because in this case, we cannot hope to recover the 2 parameters by using optimization algorithms. And one solution to the continuity issues of a transient standard divergence is based on using the Wicker metric. And in this case, we use optimal transport. And the papers by and in the papers 26 here by Goodfellows and his co-authors, they actually sorry, that's by Achowski and his co-authors. They actually propose using the first order versus time metric instead by using the transient standard divergence between the TVZ, right, and P. So what's the first order versus time metric, right? Basically, like the first order versus time metric between 2 distributions is also a special case of the Kantorovich optimal transport we have earlier. But now we choose the cost metrics to be just like L1 knobs, right, between X and Y. And why we use first order versus time metric? Because this has a very nice dual form. We go to this one later. But for now, based on the first order versus time metric, we can define the versus time GANs. We basically replace the transient standard divergence by the first order versus time metric between the DBZ and P, right? So basically, the only thing different between the versus time GANs and GANs in here, it basically we just use different divergence, right? And in this case, we use versus time metric for equation 16. And first order versus time metric is actually meaningful because even when 2 distributions have different supports, or like one distribution is discrete and another one continuous, it is still verified, right? And continuous, right? To see why it's continuous, then let's take a look at the examples we have earlier. So for examples, what's the diametric, right? The transcendent divergence between DBC and P here. We remember earlier it's log 2, right? As long as P not 0. But in this case, for what's the diametric of the first order between DBC and P is always the absolute values of the parameters. So this one surely continuous, right? Continuous function for on P. And we also can use optimization method to solve for that problems. And we can demonstrate in general that if DB is continuous, then the first order versus diametrics is also continuous. And if we have further assumption on TV, then we also can guarantee that the first order versus diametric is differentiable almost everywhere. Right? So I mean, like the versus diametric is very convenient, especially when you want to guarantee about the continuities of the loss function. And these observations indicate that first order versus diametric is a valid choice for GANs. But then if we actually directly use the definitions of first order versus diametric and we try to solve for this optimization, then it's actually not easy, right? Because we don't have the closed form, right? Hard to compute, right? So we need to actually find another way to optimize this loss function. And this is where the first order versus diametric is be useful. In fact, we can demonstrate that with the first order versus diametric, it has very nice dual function, where we can demonstrate that it's exactly similar to the subminimum of our Lipschitz functions of expectation of x from P of fx and x from Q of fx. Right? And this form here is very elegant and useful because it means like in this case, we can turn the versus GANs here into these problems, means of the parameter P and the max of the Lipschitz function, right? Of the expectation of x from the TPZ of fx and minus x from P of fx, right? And then we have two parameters. The first one is the P, and the second one is f, which is the Lipschitz function, right? And in this case, we can approximate the L1 space by using deep neural networks, right? Where we parameterize f here by f omega, where omega is the weight of neural networks. Then we can write equation 19 in terms like mean of phi and max of omega of expectations of z from bz of f omega tbz, right? Minus the expectation of x from b of f omega x. And so because everything now becomes parametrics, and also you can basically just utilize stochastic gradient descent method to solve for both phi and omega, right? And the tail algorithms you can find in the papers, in that paper 26 here. I'm not going into details about that algorithms. But then this is where we see why using the first order versus diametric is useful, because you have a nice dual form. But then there are also some limitations of a dual approach. Like the first thing is that we need to use the Euclidean, right, matrix, right? Basically, in this case, remember earlier, we need to use this Euclidean matrix here. And the Euclidean matrix is very important to have these nine dual forms in equation 18. If we don't have Euclidean matrix, then we have very complex dual forms, and it can be very hard to use. And also, like the Euclidean distance assumption is very strong in practice, because when you have high dimension data, Euclidean matrix is not efficient to capture their differences. That's why in general, we don't just want to use what's the diametric of first order. We want to use the general forms of the Kantorovich optimal transport. That's why we consider the mean phi of optimal transport between DBC and P, where we consider like general Gauss matrix, right? So we actually don't constrain ourselves to the only the Euclidean matrix here. But then, as mentioned earlier, if we use the channel cost matrix, then it can be challenged to compute directly the optimal transport between DBC and P. And we actually can, the solution here, like we can sample the data from both distribution TBC and P to approximate the original values of optimal transport between TBC and P. And this also leads to the approximation Pn, which is like the approximation of P. Right? We wrote the data x1, xn from P, right? From P, right? And then for TBC, then we also try to draw the samples Z1, Z2, Zm from the BC. Can we think like Gaussian? It's Gaussian, right? Simple Gaussian distribution. Right. So we can use the distribution here and here to approximate P and TBC. Right? And then it's mean like we can approximate the OT GANs. Right? We have in 21 here in terms of 22, which is like we try to take the inf over phi of the optimal transport between the two discrete distributions. Right? But then we actually face some challenge from computations, right? Because as we studied earlier, the computational complexities of computing the optimal transport between the two distributions, right? It actually is the order O of the max mn square, right? Okay, we studied earlier. But then because in practice n can be very large, like it's large a few millions, and m need to be very large as well. And it's mean like this can be extremely large, right? So it's not going to work because we have something like memory issues. So the solution is we can use the midi batch optimal transport GANs. Okay? And this is also very important. Idea is like we try to consider small batches of data and we play with that and we try to estimate everything with the midi batches. And to formulate that idea more formally, I also try to introduce a few notation here. The first one, like m is like we define m to be the batch size, where m can be much smaller, right? Much smaller than the original size of data points. Then we also consider that notation here to be the set of all the m elements of the data and also of the legend variables. Then we also define xm and zm here to be any set of m elements from these big set. And we also define bxm to be the corresponding distribution of the data from xm, and bcm also corresponding distribution of data from zm. Right? And then for the midi batch optimal transport GANs, MOT GANs, then we say that for any batch size m, that's equal to the mean of mn and the number of midi batches k, right? We draw data, we draw all the midi batches, right? Yeah, all the midi batches psi m, and it's also midi batches psi m from the data points x1, xn, and also the sample c1 and zm. Then we define the midi batch optimal transport GANs of this form. Consider average of the optimal transport among midi batches, right? And in practice, the common choice we usually use is case 1, right? Which is like when we have only like one midi batch. And we usually choose based on the memory of a GPU. Okay. But then the choice K1 can give you like suboptimal results in practice. And we will see that one soon. But then here we want to briefly discuss the complexities of computing the midi batch optimal transport GANs, right? So when the parameter 3 is given, then the complexities of computing the optimal transport between these midi batches, right? Exactly OM cubic, when we basically solve by using the network simplex algorithm or like some other solver. And we can improve that complexity to LOM square by using the entropic regularized optimal transport earlier. Right? It's mean like the best complexities of approximating the sum here in this midi batch optimal transport is OKM square, right? Where k is the number of midi batches, right? Number of midi batches, and m is a batch size, right? So I mean like if we can guarantee that km square here much less than the original size, right? Then the complexities of mini-batch optimal transport GANs is much cheaper than that of the OT GANs, right? And this also means, like in this case, we can guarantee that we can still run the mini-batch optimal transports, right? And we still have like good results, right? And so I'm not going to go into details how we actually can like train the models. We just go to some results. Like for example, like here we have the cyber 10 data points, right? Data, and we try different number of PD batches 4 to 8 and batch size 200. We see that the one we actually have from the media batch optimal transport GANs still give you like quite good results, right? The qualities of the generated data are actually quite good. But then before ending my talk, before ending my lectures, I also want to highlight a few issues of the media batch GANs. First thing is like media batch GANs actually suffer from misspecified matching issues. Mean like the optimal temper plant that we obtain from the media batch GANs may contain wrong matchings that do not appear in the original plant of the optimal GANs. It means like the misspecified matchings actually lead to a decline in the performance of the media batch GANs. And we see that in this case, the result here still far from the real image, right? And this is because we have these issues for media batch GANs, right? And that's also an active research areas of finding a better ways of doing media batch in practice with GANs, with optimal transport GANs. And there are actually a few proposals in recent years to deal with that issues. The first one is based on using batch optimal transport or using other kinds of optimal transport. Right? And it turns out to have better performance than the media batch optimal transport GANs because they can solve, they can alleviate the misspecified matching issues. But then there's still a lot of issues that need to be done to actually further improve the media batch versions of optimal transport GANs in the future. And so this is also the end of my talks. Thank you, everyone.